It's always an honor to be introduced by a student and a postdoc. And thank you again for the invitation for coming to this workshop and telling you a little bit about what we've been up to. So I'm going to share my screen here. Hopefully you can see it all right. Perfect. So what I'm going to do today is a little bit maybe different from some of the talks you typically hear. What I tend to like to do is sort of give you an idea of what we've done technically, but also some of the things we've learned from our experiences working with scientific workflows, and sort of lay out a little bit some of the challenges that still exist for the community as a whole to be able to address. And I'm going to be talking more in the context of future workflow scheduling, but I'm going to be touching a little bit on jobs and data and a lot of different things that are connected to workflow scheduling today. So I expect many of you are already familiar that scientific data is a huge problem right now. Berkeley lab, which is where I am, is a Department of Energy funded national lab in the United States and home to many user facilities. So what we see here is each of our facilities are producing and managing large amounts of data, but also complex software and processing. And scientific advances are increasingly depending on our ability of these researchers to harness like high performance computing centers such as NERSC, which is our HPC center, ESNet, which is our high-speed network across our facilities, and be able to operate on large scientific data produced by these experiments, observations, and simulations. So the key question my team tries to address is, how do we enable researchers to effectively and efficiently manage the computation and data? How do we manage the data? How do we manage the data and the workflows on future in-network HPC architectures? How do we manage the jobs? How do we support sort of more interactive, iterative, and exploratory workflows in the current infrastructure that we have? And how do we capture sort of this end-to-end scientific process and enable sort of data and workflow sharing, search, and reuse? So traditionally, at least from the time I was a graduate student, what we've seen is simulation jobs have dominated our workflows at HPC centers for many decades. In order to run these workflows in HPC centers, what users usually do is submit a job through a batch queue system like SLUB, and typically users specify job dependencies explicitly through these batch schedulers, or have these external services that run workflow managers that then sort of distribute the jobs and things like that. So most of the work around workflow scheduling started in the days of grid computing, where we sort of ended up with two-level scheduling, right? One was at the site selection level, where do I run at Argonne or do I run at NERSC? And then you sort of had a little bit more in the batch queue scheduling. You had various batch queue schedulers that have evolved over time, trying to address a lot of the questions around how do you manage these large simulation jobs. So the concept of workflows, I think it's important to mention that sort of evolved from this concept borrowed from the business community. So many of the workflow tools developed in the community has its roots in specific scientific domains and focused on sort of this idea I just talked about around grid resources and distributed resource management and application-specific needs for those. We've seen a lot of momentum around workflows in the community, but at the end, many of these workflow tools sort of assume that directed acyclic graphs are sort of the way to manage and represent these workflows. So what do we do with the data in these workflows, right? We put a simple arrow and we hand wave and pretend that the data is a black box, and we can largely ignore the details of the data and just focus on the data movement. And a large focus is really around how do you get this computation running? And there is sort of an assumption that the infrastructure is a black box, and HPC centers have a batch queue, and we just need to submit it through the batch queue, and you get some results back. And so there's been sort of a little bit of a disconnect between communities, between the workflow community and sort of the HPC infrastructure facility community, But there's also sort of a little bit of a disconnect around what's your important metric, right? Workflow as a concept is a productivity construct, but as a community in the HPC community, we're looking at performance as an important metric, right? So this is a little bit of background I wanted to start with. So, but the reality now is we're beginning to see more and more data processing and analysis workflows running at HPC centers. So the pipeline here, which Anna and my team ran sort of about a year and a half, 2 years ago, at the start of the pandemic, is an example of a recent workflow where they are analyzing and mapping the structure of COVID-19 proteins using HPC resources. There was a significant number of changes that needed to be considered while designing this workflow for an HPC. This was a workflow that ran in somebody's desktop and on a local HPC, on a local cluster. But it was a complex set of software. So we kind of relied on containers, especially because we had a time constraint on trying to get this run in time to be able to inform the science around COVID. But we also had to do a lot of work around managing how the jobs are executed, managing the IOs, and sort of reducing sort of redundant writes and reads and things like that, right? So this has sort of raised some important questions around these type of workflows, like experimental workflows, and how they are supported in HPC systems. How do you support sort of their needs for a timely analysis? How do you coordinate these workflows across organization? How do you do the data networking and data movement? And how does the job queue interaction work? So thus, in reality, what we have is we have a lot of heterogeneous and complex workflows now running at HPC centers like NERSC. And data is manually moved between these storage systems. The resources are managed for jobs and not workflows. Large amount of data is moved in and out of these HPC facilities now because people bring their data, process it, and sometimes move it back. However, these workflows can also be created sort of implicitly, right? They may have a workflow manager, but often we'll see that they're thrown into job scripts. And there's a gap between how these workflows and structures sort of are managed on these HPC systems. So we don't have a global view of these workflows. What we see from an HPC viewpoint is what that batch scheduler view looks like, which is a series of jobs. So a long time ago, when Gonzalo was working with me, we started asking ourselves this fundamental question of, can we break the current mode of considering HPC as not as a black box, and can we improve how workflows are scheduled on HPC systems, right? So there were two modes of managing workflows on HPC systems. First is what I call the chain job approach, right? Where each step of the workflow is considered as a separate job in the batch queue system. This is great, except this results in ridiculous wait times between the stages in some cases. And so people started sort of looking at it differently and said, so maybe I can just get sort of this large resource allocation for my entire workflow. So in the second method, there was sort of this concept of you'd submit a pilot job where a single job encompassing the length and breadth of the job was submitted, and you would be able to use that. But the problem with this is the breadth of the workflow changes, right? The first task on the workflow may need only one node, whereas when you're doing a large sort of parallel analysis, you need a lot of nodes, and then sort of bringing it all together. So there was a lot of resource wastage that you usually see there. So Gonzalo effectively implemented sort of this idea of a workflow abstraction in the Slurm scheduler, where all the priority of all the jobs in a single workflow would be considered as a single workflow in terms of scheduling. So the beauty of this is, we didn't modify any algorithms. We were able to show through our simulation that we can get about 4x the speed of real workflows in a NERSC type workload from that time, which is around 2014. All right, so the other part of this is, I talked about this idea that, we need sort of this elastic resource allocation, right? So, cloud computing had been around. People sort of liked this idea of how you could get resources on the cloud and then take it and to grow or shrink your resources as you needed. So some of our work in that time frame was sort of looking at, how do you build elasticity in an HPC framework, right? So we built sort of this, built this framework where we use checkpoint restart as the underlying mechanism to grow and shrink your resources and migrate workflow execution across the dynamic window of resources, right? This is, it had negligible overhead but there is sort of the cost of checkpointing that we do need to consider, and it may not be the right solution for every workflow, right? So this was a great piece of work, but we were also looking at data around that time and sort of trying to figure out how to layer data on top of the workflow abstraction, right? So what we did was, Devarshi, who was in my team, sort of looked at this idea of a virtual data space that provides a way to manage data while hiding the underlying storage system. So data management strategies in MADATS leverages sort of this multiple storage layer because it sort of considers an abstraction over it, and you can map the data elements and the workflow elements. So you can sort of schedule both the data and the workflow together on different types of compute and different types of data, right? So we were able to show it scales. This is kind of classic work looking at how to manage the data memory storage layer. So around this time, we were sort of also realizing that there was a little bit of a disconnect between some of the things we were doing on the research side and how our users were perceiving this. And we started sort of asking ourselves if we could use this concept of user research, which I'll come to in a little bit, to understand sort of how the users are approaching work. But many years before this, I worked on a project called the North Carolina Bioportal, where we built a web interface that supported bioinformatics, right? And what I realized when we finished building it and we were holding some training sessions is a lot of people were actually sitting there and running an application on the browser, copy pasting that output to a notepad, and then pasting it back into the browser to run their workflow, right? So there were some important lessons here, which I didn't know at that time, which is, knowing what the users are doing and their work practices around the data and workflow is important. I may develop the best scheduler, but that's not useful if, the user is relying on a certain mode of using it, right? So more generally, what we realized over time was the scientific process is sort of like being in a kitchen. It's an analogy that one of my social scientist collaborators likes to use, which is you often follow a recipe, but you kind of improvise, right? You're like, yeah, my family doesn't like too much spice. I'm going to reduce the spice on this. I'm going to increase something else in this recipe because I like this, I feel like this could be a little different. Also, when your food is cooking, you often do the dishes or clean the kitchen or deal with homework or whatever else it is, right? Similarly, the scientific process is highly variable, ad hoc, and it's not sequential, well-defined process, and it isn't completely represented in DAGs, right? There are many hidden steps in this process. For example, in the workflow here at the bottom, there's a lot of invisible work going on around data cleaning and QA/QC that isn't represented well in a DAG, and data is not neatly arranged, as you can see in my other diagram where this shows a screenshot of someone's desktop. It's a lot of information in people's head. So this has sort of helped us think about workflow scheduling, data scheduling in a very different way, and sort of trying to solve a different set of problems, right? So I touched on this briefly, but there's also a lot of information in people's file names and human brains, right? A lot of supporting artifacts and contexts are not captured. So we don't capture the notebooks where people might be writing down stuff. We don't capture sometimes the data that's sitting on external hard drives. these human consideration and constraints don't make it to that represented data that we computer scientists see. And this is going to will change how we think about scheduling, because we may not actually know everything that the user is trying to do. So last but not least, when we build software or we build new algorithms and new schedulers, often the collaborations have complex software stacks, and we find that they try to keep to a minimum common denominator, right? So a lot of sites will say, oh, I don't use the scheduler dependencies to submit my workflow because I cannot run it at this other site with that same. I would have to make a lot of changes, right? So the bigger reality here is new work practices that don't fit into current work processes, they often don't get adopted. And it's something we need to think about as we build these software pieces. So what we've done over the last 10 years or so is we've started taking a dual approach to addressing the challenges of scheduling, workflow scheduling, data schedule management, and things like that in scientific workflow. What we do is we work very closely with application scientists to develop methods and tools to manage their data and workflows, and with the HPC center staff and the system software, right? So I have social scientists who actually use user research methods to interact with these groups to try and abstract out some of the requirements and constraints that come which are not explicitly mentioned in other situations. So user research, what is user research? User research is being used to design our phones, all the websites that you use, to understand how the user is using it. And it's, in a way, it's sort of a process to verify and validate your intuition about what the user needs, right? And convert it into action. User research is both a science and an art. There are people who are trained to do this, and having them on our team has greatly enhanced what we do. I'm not going to go into this in a lot of detail, but basically this is very similar to the scientific process. You discover and explore, you synthesize the data, the qualitative data that you get, you use that to design mock-ups or sort of conceptual architectures that you then go back and do some usability tests with the users, right? So this is very similar to what we do in computer science. It's used a lot in industry, much less in the software and the academic fields when we build software. I strongly urge you to consider that as you think about your research. So as a quick segue, we did summarize some of our findings on creating usable software for science. And often what I find is we're not solving the right problem, right? So I, very early in my career, I used to work a lot with the Advanced Light Source. And we wanted to build them a fancy workflow system to some extent and solve their hard data and workflow management challenges on an HPC system. But they had a fundamental problem, which was they had all their data sitting on an external hard drives, and they were running out of budget and unable to manage the system, right? So it was useless for me to build anything else till I solved this problem first, right? So it's important for us to, as researchers, to sort of think about where in the spectrum we are and how we can sort of bring people along so that we can move them to the next stage. The other one that's important is understanding the context of use, right? I may have this vision of someone's going to run their field site workflow on an HPC system, but that picture there shows them, submerged underwater trying to correct observations while they have almost no signal. So how are they going to run on an HPC system, right? What do we need to do to manage their scheduling and their sort of general infrastructure? So the last but not the least, and coming to sort of what I think is important for this community to think about, is we need to think about what the users' metrics are. I have a hint here, and I'm going to go into it a little bit more in my next slide, but it's usually not performance, right? So we as a community we focus on performance and time a lot, right? We're talking about when we look at this workflow of what people are doing, we talk about the allocation and the preparation of their jobs, submitting it to a queue and execution. And we're always talking about optimizing the time, optimizing the performance, right? But the reality is, for most of the people, they're not thinking about this the same way. There's a human element and a human time that goes into decision making. Very early when we started doing user research, one of my staff entered into my office and she said, "Oh, we have a problem." And I said, "What's the problem?" And she said, "I know you want to optimize all of this, but the scientist just told me he isn't going to he knows how to optimize his code base where it would run in 4 hours instead of 8, but it doesn't affect his life because he launches his jobs in the morning, goes off to do work, other things, and coming back and just checking the results at the end of the day, right? So he isn't going to optimize his code because finding that time to optimize the code is much harder than just letting it run a little bit longer, right? So it's something we have to think about in terms of, if we won't be able to solve the next generation scheduling problems till we talk about this metric disconnect, right? Which is what they care about is their human time and their science results, and what we are caring about is the performance and efficiency, right? So this is something that we're going to have to, as a community, think about a little bit more. Cloud computing, it was introduced around the time I was a postdoc, and it is an important as part of this field, right? Of, how are you managing? Can we use cloud computing or the cloud computing models to solve some of our problems? Cloud computing does tend to take productivity as a metric a little bit more than maybe a traditional HPC system does. But we did this long time ago in 2010, and I do still believe this is true, which is they still require a significant programming and system administration support that we are not quite there in terms of making that available to an end scientist user, right? A lot of the scientists are programmers, but not in the same extent, and don't necessarily understand system administration in the same level. And I think that's, it's a little bit different in the commercial sector, where the people using the cloud are usually traditional developers, whereas we have a lot more mix of roles in the scientific community. But given, cloud computing, some of our results from Magellan, we definitely seen this push towards how deploying container environments in HPC systems, right? Spin, Singularity are container technologies that are used in some of the HPC centers in DOE. New systems like Perlmutter have considered container technologies based on Kubernetes right in the get-go, and sort of setting aside nodes to do that. However, there's still some challenges in performance when you come to looking at containers, especially when you're looking at sort of data and data uploading and things like that, right? And so, for example, one of the projects I work with is called ESSDive, which is data repository, and they found that their system was performing significantly slower when they were trying to upload large files. And what we realized is, having a dedicated container on a node was better than having on a shared node. But still, this was still slower, especially as you went to file sizes that were bigger, right? And these are issues that real projects face, and the architectures that we're building are not usually flexible enough to allow users to pick and choose and make this more programmable in a way that might best fit their requirements. So, we learned a lot of things here. I've been hinting at some of the social issues and stuff like that, but I do want to spend a few minutes here talking about what the user perceptions on HPC systems are. Drew and Sarah and my team have looked at this for many years, and what we've realized is abstractions, which we love as computer scientists, may or may not improve usability, right? Middleware tools frequently hide sort of what the scheduler is doing or what a storage system is doing. And our users continuously tell us about how that isn't completely useful because they don't understand what's going on. So when there is a breakdown, when there's a failure, they cannot fix it. And most users have to at least be able to debug to an extent to know where they can go ask for help. And a good example of this was a task farmer that we deployed at NERSC many years ago. And our users basically said, that's great that you figured out how to farm the tasks. But at the same time, when it breaks, I have no idea what's going on. And that's not useful, right? So transparency upon demand should be a key design goal for our software, scheduling software, and other things that we build. The other thing that I think was a little bit surprising to us here was we've assumed to some extent that there is, very expert users in HPC who've used HPC for many decades. And then you have sort of the new real users who are still learning, right? But what our users basically said was they were perpetually learning how HPC systems function, right? Because there was changes in hardware, changes in software configuration, leading to uncertainty, and sort of building the relationship to align scientific and computing data worldviews is necessary to enable that productive use of HPC system. We also find that there's sort of a disconnect in sort of timelines of adoption of new technologies. There's an unreliability of new feature and necessity for adjusting their code. So a lot of projects don't adapt the new and the features that we deploy, right? They want to sort of see if this is going to last. They have to align with project cycles, which are often different from the infrastructure cycles that we have at HPC system. So I'm going to take a little bit of a deep tour here, take you a little bit again to the past. So I went through the past, came back to the future, sort of going back a little bit, because I think history is who we are and why we are the way we are, right? So it's important to understand what's happened on our HPC systems, what's going on, and being able to do a retrospective analysis on our logs. So some of this work initially started actually with Gonzalo again, where he was studying the 2014 workloads. And what we found across 3 systems at NERSC was the job workload times were on all 3 systems were, significantly lesser than one would imagine, right? They were less than 2 hours for about approximately 85% of the jobs. There were also a significant number of jobs that weren't using a large number of nodes. 30-ish, 35% were using about 1 node. And there were, about 10 nodes or fewer that was very typical for a workflow, right? And then 60 to 66% of the HPC system and 95% of HPC cluster jobs run for less than 50% of the requested time. And jobs often overestimated their wall clock time in the case of 10% of the jobs, right? They ran over their wall clock time over 10%, about 10% of the jobs, whereas 50% of them, didn't actually use it, right? So our user research team, over time has been looking at this and trying to understand why do people pad their wall clock time, and why are people how are they dealing with the queues and things like that? And this is very interesting because a lot of our users basically tell us that there's enough variability from the IO system and other things, so they like to pad their time on the wall clock, even though that means they may wait longer in the queue, right? But they prefer that to their jobs failing, and so their estimations are often wrong. What this also means is, we often use that as our criteria for how we schedule, and it's not necessarily always, maybe not the right criteria in some HPC centers. There's sort of also unpredictable queue times and abstractions, right? So one of our users was very confused because they were seeing a lot of variability in queue wait times on the debug queue, which is a queue that's used to test programs and guarantees a quick turnaround, right? What the user had forgotten that the reserved node pool size for this varied over the course of the day, right? So it had about 512 nodes in sort of the peak day, 5 a.m. to 6 p.m., but it had only 64 nodes in sort of the late evenings, right? But a lot of these, there's no time for science, right? We do it all through the day. And while these policies were available on the web page, the user not being able to see this when they were submitting to queues and stuff was sort of a breakdown of how they were perceiving queue wait times and things like that. All right, so moving on here a little bit, we also have done a lot of work more recently, sort of saying, we know there are jobs in workflows, but we know as a concept there's jobs in the HPC system, but there's concept of workflows exists in the science community, whether it's implicit or explicit. So let's look at these job logs in a different way. And we've had two sort of different methods we've tried out, where one is we've looked at the IO dependencies to see if there are jobs which use the same IO file in the next job, right? So in theory, those would be a workflow in the DAG that we usually represent. But the other one was also we looked at sort of the more time window aspect of this, and we realized that there were sometimes a lot of different jobs that a user would sort of dump into the queue, and they were in some sense, in their mind at least, related with sort of a campaign or sort of a particular data set or something like that, right? So we did some analysis, not just looking at jobs, but also looking at sort of this concept of a workflow in the job queue and seeing how that looked like, right? So what we found here is the resource usage for what we call a single job workflow, right? Where a single job workflow is all steps of the workflow are within a single job script, right? And they tend to be different, and they may have multiple SRUNs or multiple ways jobs that processes are lodged within that script. And what you see here is, we have different types of workflow where we say it's fixed, like they use the same number of CPUs, or they scale down and scale up, or a mixed, they do some mix of scaling up and scaling down, right? We looked at both the time window and data dependent workflows, and we found that generally there was an underutilization in both cases, right? The single job dependent workflows, they oftentimes they put in a fixed number of CPUs in their job script, which is why there was an underutilization. And this calls for sort of better scheduling policies and mechanisms, right, that allow us to manage the resources more effectively. And so this is something we should, as a community, be thinking about. And then in terms of workflow runtime affected by job level scheduling, this graph here shows a heat map of the number of workflows grouped on the basis of workflow runtime and the maximum node request by that workflow, right? This graph specifically focuses more on sort of the parallel execution pattern, where unlike the data dependent parallel workflows, many of the time window workflows with parallel execution patterns had longer runtimes. This result, largely can be explained based on the fact that the jobs often run sequentially, although the users submit those jobs in parallel, right? So there's an opportunity to use knowledge of that workflow structure across jobs in a batch queue system to improve scheduling and hence better turnaround times for these workflows. We have more detailed results in the paper, so I'm going to skip over that at this point. We also have sort of a programmable infrastructure that we are sort of aiming towards, where we envision that a workflow is able to sort of allocate the storage and the network and the scheduler for the job computation. And we were looking, one of the ideas around this is sort of looking at the data movement and the job connection, right? The synergy between that. And we found that 60% of the users usually transfer data in and then submit a job within a day. And similarly, 80% of the transfers that are going out occur within a day of a job submission, right? But a large number of these are happening manually, where the job submits, the user goes, checks, and then they resubmit the job. So at this point, I've given you sort of a look of various things we've done, trying to look at the various aspects of this. I want to switch over to sort of looking forward a little bit here. I think I have about 20 minutes on my talk. So I'm going to spend a few minutes here and then leave a few minutes for questions at the end. So I want to start here with sort of an example and some of the challenges we think about that's coming our way. This is from my collaborators, Charu and Yushin. And today, 60 to 90% of the water resources originate from mountainous watersheds. The Earth Sciences at LBNL, they lead the sort of the world's most comprehensive mountainous watershed testbed, which is the East River in Colorado. As you know, those of us in California living in a drought worry about water a lot. And we believe that the science here is important, which is it's important to get finer granularity measurements by changing the setup based on some intelligent decision making, since uncertainty is great as snow melt dominated systems move to low or no snowpacks in the futures. So the long-term vision here is to be able to bring together the data from a field site, have controlled lab experiments coupled with sort of the models running on an HPC system to allow for a self-guiding field observatory for natural resource management, where you can figure out what you want to collect data on, how you want to collect data in a much more dynamic fashion than what happens today, which takes months and sometimes even years, right? But there's some distinct challenges here, especially in terms of managing the data and the workflow. For one, the network connectivity is spotty at best. We have 5G systems being deployed, and the region isn't accessible for multiple months of the year because of the weather conditions, right? So we need to be able to develop our models to run on the edge, and have some kind of mechanism for it to communicate with the HPC system when there is connectivity, and be able to use the local data and sort of this global workflow in the decision-making process. So this was just one workflow that I described. We have a number of them at Berkeley Lab, but the National Academy of Sciences recently released a report that also talks about this problem as being a key driver for us going forward, where computing and automation technologies can now also control the acquisition of data through the design of new experiments or decision-making about new observations, right? So how does this look like from our world? I do envision that we have an autonomous discovery and science loop, where you have some instrument science, you have some edge computing close to it. You need to manage the experiment instruments, sample preparation happening there. You have sort of modeling, which is the more intelligent decision-making, which might be a digital twin or modeling simulation, active learning, AI, ML. And the key core that, of course, this community and I'm interested in is sort of this distributed workflow of how you bring that instrument science and the intelligent decision-making together. How do you manage the data and computation at the edge, HPC, the streaming data analytics? What kind of hardware specializations do we need? And how are we going to make this cost-effective, efficient, and usable across domains? So some of the key questions that come up when we're trying to build this architecture is, so how do you manage and schedule resources for data services, right? Science Search is a project that we have here looking at sort of extraction of metadata, where we use AI models sort of to extract metadata from various artifacts. And one of the challenges we are facing is sort of, where does this run on an HPC system? Right now, we deploy it at the edge of the HPC system on the container technologies, but we kind of had to use the high-performance file system as well as the batch queue for potentially running search as a job type. And there's often the what we find is there's sort of uneven load balancing and things like that we need to be moving towards fixing for being able to schedule and manage sort of these data services in conjunction with other workloads that we have at HPC systems. The other thing that's really changing our paradigm is we are seeing a lot more interactive, exploratory data processing and analysis on HPC systems. It's very common now, and I have an example here from the Materials Project and Advanced Light Source, where users want to come in, bring their data from the modeling and experiment, use things like Jupyter notebooks, run these data analysis jobs on HPC systems, interact with them in real time, and then make decisions about what they want to do. But they also want to use the stack, and they want to collaborate and have multiple people looking at the data, often again in real time when they are sitting at the beamlines collecting data, and be able to reproduce these workflows by different users, even by them, when they're done with the data collection and they want to do a much more deeper analysis, right? Sort of building these software stacks is going to be an important thing. One of the things that there's been a lot of work that we are engaged in and the community is engaged in is sort of looking at parallel tools like Dust to run that in an HPC environment. And this is still a major challenge in terms of how do you get the performance and the robustness that you need, where you can do this in a much more interactive way and move away potentially a little bit from the batch queue model that we have traditionally seen. So data services are, as I said, are going to be very critical, whether that is, things like Jupyter notebooks learning on the edge of HPC, or, things like search infrastructure, or tools that provide reproducibility, findability, things like that, right? There's a big question here still on sort of where do these purple boxes lie, because we have this, we need the compute to be close to the data. Do they sit in the HPC center? Are they a little bit different, and they provide a gateway to the HPC center or cloud resources when they need more computation, right? We sort of are in this paradigm between large data, some compute, large data, large compute, and then what we've traditionally had, which is much smaller data and large compute, right? Sort of how do we sort of bring these together to build an infrastructure that would serve the needs of a diverse set of users? So what's really happening is we need to start taking a close look at HPC and distributed software stack, right? We need to be able to go beyond what we've had, which is what I call the three sort of horizontal stacks here, which is the experiment and observation, the network, and the HPC system, which itself is layered on our general stack on each of these layers, right? You have the systems, you have user tools, you have applications and web interfaces. But this is kind of getting mushed together, and we have additional things happening where we have these services between the network and the HPC systems. We have edge computing, and between the experiment and observation and network. And these boundaries are merging, where we need to sort of consider a horizontal and vertical integration of resources, infrastructure, scheduling mechanisms, and things like that. We need to start thinking about the scheduling considerations that more wide area, things that are explicitly and implicitly associated with a scientific workflow. And I do believe that software is going to play a key role in sort of this future integration and innovations, right? Dan Reed and Dennis Cannon and Jack Dongara just released a report about some of the challenges we're seeing with innovation in HPC hardware. And we're going to have to layer this on top of sort of a much more software infrastructure that serves the needs, where the infrastructure itself is self-driving and responsive to sort of some of the autonomous needs of science, where you can have that loop happen, right? So I want to sort of leave on this note of, I think there's a lot of cool key research that needs to be done to support science. We can definitely learn from industry, but there's some challenges that are very specific to our environment. And I have to thank everybody who's worked with me over the years, and our funding agencies who've helped fund these efforts. And I'm ready to take any questions.
Thank you very much. I have one. Gonzalo have a question, and I have also a question.
You go first.
My question was more, well, general and not very technical, but I like the part at the beginning where you spoke about your experience with, how to put it, that you need to communicate and learn how your users are using the workflows, that the workflows that they are using are in their brain and cannot be directly mapped to docs, to put it simply. So do you have some, let's say, some golden rule how to approach different users when you want to, let's say, optimize the way they are using your infrastructure? Like, I mean, like for some users, it's perfectly okay just to tell them, look, here is a perfect documentation, and this will help you improve your experience. For some users, you need to actually do the work for them because they are not able or not willing to fix their scientific tool. Sometimes it's just it's not their fault but your fault because you really don't fully understand what is the difficult part in their job. So my understanding is that you have a lot of experience with this. So do you have some idea how to what steps need to be done if you really want to, improve the cooperation with the users?
Absolutely. I do have a lot of thoughts on it, and I have a whole different talk I can give on that, but I'm going to give a quick answer here. So one is, I think you can get a lot by just sitting and listening to the users, right? Which is often what we do is we go to the users, and I've done this all my life, right? Which is go to the user and say, I have this cool new thing for you. But just going and asking an open-ended question, which is what the user research people do, which is to say, tell me about your work, tell me about your challenges, right? You will learn a lot from that process. The other thing that we like to do, and we do this not just for user interface, traditional user interface like web interfaces, but also command line tools and stuff, is we do usability tests, right? We take 2 or 3 different users who are at different expertise or different needs, and we just ask them to do simple things, right? Follow the README and go, and I'm just going to be on Zoom with you, watching you do it. And you'll be surprised. And just, there's only one thing we tell them, which is just talk aloud when you are thinking about how you're thinking, right? And you just stay quiet and watch them, and you'll be surprised at how much you learn in that process, right? These are quick things that I think every one of us can do. I'm happy to talk more offline, of course, about how to conduct some of these. So user research people are trained in this, but I do believe all of us should be able to do this to some level as we build software and tools.
Thank you. Yeah. My experience is similar. That sometimes people want to write the perfect documentation and then have, then they don't have to care about users anymore because it's all there, and it's like, no, it doesn't work like this.
It doesn't. Never does.
Thanks.
My question was also quite general, since you have such a wide and deep view of infrastructure and interdependencies and different systems that interact in the academic environment. what share of that infrastructure is more service oriented and what share is more like batch oriented, and how those are changing?
That's a good question. At this point, I'd say what we have is largely a batch-oriented system with service-oriented at the edge with a very, very small percentage. I do think that will need to change. I think the big question, which is not really a technical question, is, how does this get funded and where are the boundaries, right? Who runs the service-oriented architecture, and is it just at an HPC center? And I don't think we know the answers to that yet. I think there's some advantages to doing it at an HPC center and leveraging some of the capabilities at an HPC center. But there are a lot of sciences that need the same service-oriented architecture, and they don't need HPC, right? And so the question is, how does that service-oriented architecture, where does it sit and what does it look like? I think those are questions we are currently asking ourselves and trying to figure out the answers to.
Thank you.
Somebody, James had raised his hand. Do you still have a question, James?
No, it wasn't so much of a question, but it was to speak on the point that Dalibor mentioned, going back to your sort of learning how your HPC users use the system. It just kind of struck a chord because the way that we work at ILM now for developing software and the render farm improvements we made follows a new kind of agile programming or agile project management that actually puts users kind of in the driving seat. And so the way we were working is that we have like an elected product owner, and they speak for the users, and they're kind of like the conduit, as it were. So they go and speak to the users and figure out how they are using the system and their woes, their challenges, etc. And then we have meetings with the product owners, and then we have a session where we're trying to determine the priorities and rank the priorities of the work that we need to do to improve the system and things like that. And it's a very iterative and engaging collaborative process. I don't know where I'm going with this. I'm just trying to sort of add some weight to that argument that you do have to have your users at as the key heart of improving any kind of system. And
absolutely,
this is one way in which we started doing it. That if you don't read the paper that we've presented, just skip down to the bottom and there's a references link, and it's about how this how we've adopted using this cycles, as it's called, agile methodology. Is quite effective.
Absolutely. I would, in that note, going back to the question and discussion we're talking about, which is, I would recommend the Lean Startup book, which is where I first sort of picked up the idea that, how do you get users in the loop, and how do you sort of pivot as you learn from the users, right? There are other usability books that are also pretty good. I'm happy to, if someone wants to send an email, I can send other links that we found useful to just start thinking about this in our cycles, right? Of whether it's research or development. So I'm happy to see y'all are using it too, James. I also would encourage, if at all possible, to have the developer team watch that process as well. I think it was mind-blowing for a lot of people, the researchers and developers in my team, when they've sat in on one of these usability tests and what they thought was the perfect system they had built, which is, just got shredded in the first 5 minutes, right? So it's useful to do that.
I just wanted to back up what James said, that sort of product management approach and having someone who is sort of the advocate for the customer and sort of the bridge between the development and the customer, it has been the most effective way that I've managed this in my career. So I'm from Meta, and that's what we do there. We have a very sort of strong infrastructure product management team at this point. And the challenge that I see, for how that works, maybe at ILM and certainly a place like Meta compared to sort of the academic environment, is we have a pretty limited known set of workloads that align with our product lines, right? And so you can have a product manager, really conceptualize and understand in depth a limited number of use cases and really advocate really well. What I see in sort of what you're saying about the academic environment is that, you know, you may have workloads that are completely disparate from, you know, research program to research program, and that's kind of one of the bigger challenges there. I wanted to say though, I just one comment about your talk that I just found fascinating is this idea of sort of delayed analysis, this idea of sort of like having to completely separate data collection and modeling. Is just, you know, my entire life is runtime, real-time internet technology. And so for me, that's just a completely different world. So, you know, I found that really, really interesting. And I, you know, when I think of some of the real challenges about sort of the scientific community compared to, you know, certainly telecommunications, that this is one of the really key differences. And that, you know, having tried to do like cold start data center sort of data loads, like I really appreciate how hard it is to keep a data set stable and consistent with the technology that you're going to run for the model and so on. So yeah, I just found that really fascinating. Thank you.
Thank you. Thanks for sharing your experiences.